Hello? Okay. So before we get started, just a quick announcement that the final project proposal is due tonight at midnight. Yeah.
Okay, hi everyone. Yeah, thanks for being here. Today it's our great pleasure and honor to have Kevin Murphy here as our guest speaker today. So Kevin and I, actually, we go way back. We were office mates as in grad school here. So that's on the fifth floor. Yes. So it's great to have Kevin back. And Kevin has done a lot of fantastic research in the area of machine learning and computer vision. And Kevin has written the book, Machine Learning, from more of a Bayesian perspective. It's one of my most favorite machine learning books. So I recommend all of you to check it out when you have time. And Kevin will talk about probabilistic models for images and text today. Thanks.
Great, thank you.
Oh, and Kevin is leading a research group at Google Research.
Yes, great. Is that good? Am I right to move it?
Yes.
Okay. Yeah, thanks for the invitation to speak. I haven't stepped inside of Soda Hall in a long time, so happy memories. So I'm going to give you, since this is a class, I know I was told you're all somewhat experts in deep learning, but I didn't want to just do a super high-level pitch because you want to get into some of the nitty-gritty. So I'm going to just cover 4 papers, which is less than I usually squeeze into an hour. but they're all related to images and text, which I think, Trevor, you had a class just on images and text, or language and vision more generally, right?
Reading group.
A reading group, yeah, a few years ago. So this is sort of a side interest of mine. My team at Google focuses more on the image side of things, and some of the, I think almost all of the work I'm presenting today is projects that I've done with various interns and Googlers, but it's a little bit peripheral to our bread and butter, but I think fun anyway. So the first part of the talk, I'll talk about discriminative models, so mapping images to text, so image captioning, in other words. And then the second part of the talk, I'm going to talk about some very recent work that was just accepted at ICLR, which is a generative model of images and text. It's a joint probability model, which means that we can generate images from some latent representation of the worlds, which I'm grandiosely calling thoughts, and we can generate text from the same model. And of course, since it's a joint model, we can do anything, right? We can condition on an image and infer the latent state and generate language, like we did in part 1, or we can go the opposite way, which is really fun. So we can condition on language, infer the meaning, and then generate images. So just, what did they say? Spoiler alert. The work I'm going to show when we generate images is really just generating MNIST kind of images, so like digits, not real images. And we do still obey as well, but we can't generate images as complex as this yet. And also the text that we're looking at is like attribute vectors rather than natural language sentences. So it's very much an iClear paper. But I think it's interesting anyway. So we'll get to that at the end of the talk. But the first part, I'm going to talk about image captioning, which is working with more complicated data sets. So I'll just review very quickly current methodology. In fact, I remember, boy, when was this? Let's see if we have some dates. 2015, yeah. There was just a renaissance, or like an explosion, early 2015, and Trevor actually organized a meeting. And it was like, I think the last time I came to Berkeley was in 2015, and it was in that room across the corridor. And various groups were presenting. So some folks at Berkeley and Google and MSR and Stanford simultaneously, and I think Toronto, probably others too. Yeah, someone at Baidu simultaneously came across the same idea, which is, oh, let's treat image captioning as a translation problem. So I really don't know the background of you guys. Who has not heard about this kind of stuff before? Okay, everyone knows this stuff. Okay. Anyway, so it's fairly, maybe you've even talked about it in the class. I don't know, I didn't look at the webpage. All right, so this is sort of classic now. It is 3 years old. So anyway, it seems to work really well, and I'm sure you've seen these kinds of results. It was like front page of the New York Times, or at least the technology section. But as you know, it doesn't, when you start probing it a little deeper, it doesn't really work that well. So this is saying 2 dogs at play, and obviously there are 3, arguably there are 4. That's already interesting, right? Should you say 3? Should you say 4? I don't know. People might disagree on that, because this dog might not be worthy of mention. Maybe it isn't even a dog, I can't tell. And then there are some really embarrassing fails. And you know, I work at a company, right? So you know, we like to show state-of-the-art results on benchmarks, but we also have product teams who really like to get this stuff out there. And so one of the teams that's interested in this is the accessibility team that tries to make the web and other Google products accessible to all users, including visually impaired. So they would like to automatically caption images so that if you're doing a web search, you can at least get some idea of what you're looking at. And they can't, they just are so scared to launch this technology in its current state, because it might do things like this, or you could imagine it could get arbitrarily worse. And I think, you know, Microsoft was perhaps a little braver, and they have released some things like this, and some of it's backfired. So it's just not robust technology, right? Some of you might have heard Ali Rahimi's talk at NIPS, and he was just saying the whole field of deep learning is in this rather precarious state right now. But so that's one of the things that's motivating this work. So one of the key problems here is that there's no good way to evaluate performance, right? I already mentioned this in the context of the dog captioning. Is it 3 dogs? Is it 4? You could say more or less things. I could mention the green grass or not. I don't know. Is that better or worse? You know, you might be able to describe the scene but not understand many aspects of it. So it might sound like beautiful text, but it's sort of not related to the image. And how do you measure that? And it's just describing the whole image. It's not grounding it spatially. So there's various issues. So in the work I'm going to describe here, we wanted to tackle the first problem, which it seems to me the most fundamental. You've got to have a good metric that you believe is correlated to what you care about, before you can make progress on the algorithmic side, or even on the data collection side. So we turn to this idea called referring expressions, which is an idea from the linguistics community, which is the following. So the key idea is that you want to think of language as something between at least 2 parties, right? It's a communication device between 2 agents, or 2 or more agents. It's not just something an agent does in isolation. That doesn't make any sense. Right? So you have 2 agents. One sees a scene and is trying to refer to an object or a region or something in that scene, and has to describe it verbally to a listener who is listening to that description and has to infer what it is you're talking about. So which of the objects did you mean? So in this example, maybe they both see the same image, and the speaker has in mind this guy here, and he says the man who is touching his head. The listener hears that and says, oh, you mean this guy on the right. Now, if the speaker had said the man wearing blue, it would have been ambiguous, so that would have been a bad expression. So the nice thing about this task is that although it's mapping images to text, the metric is basically classification error or squared error, because you can just decode that text and see which part of the region the listener clicked on. And if it's close to what you had in mind, then you get points. So it sort of removes all the subjectivity from the measurement task, and it gets at this notion that it's really a cooperation between 2 agents. So we're not the first to propose this as a metric or as a problem. But what we did do is come up with a new way of training models of this form. And this is back in 2016, so it's, I guess you could call that old. But so the baseline approach is the following. So we're actually using a finite number of image regions. We have a region proposal generator, I forget, like 10 or something. So it's a fixed forced choice experiment. And the speaker picks on one of them randomly, and it has to generate a caption that describes that one. So the baseline would be we just repurpose existing image captioning methods, like I showed you, the New York Times type stuff, where we extract an image region and we push it into use it to condition an RNN, and we generate strings. And we can extract features from the region, and we can extract features from the whole image to give us some context. So that's going to be our baseline speaker model. And we're going to train that to maximize the likelihood of the text given the image, assuming that we have paired data, image-text pairs. So, and then the main change we made, and it's super simple, is we're going to keep the model identical to prior work. And we're going to use really old, simple model, which is just this RNN, CNN thing. No attention, no auxiliary signals like object detection. Just very simple model, but we're going to change the training objective. So the idea is, instead of maximizing the likelihood of the text given the region, we're going to maximize the posterior probability of the correct region given the text, on the assumption that there are multiple candidate regions that you might be referring to. So the posterior of the correct region is the likelihood times the prior normalized, right? The prior here is uniform, so it's just this likelihood ratio term. So in this example, if we have two regions, purple and green, and I say the man in blue, the likelihood of the man in blue is basically the same for both possible regions, right? So the ratio here will be, 1 over 1 plus 1. So it's 50-50. So the posterior probability is completely ambiguous, which is very intuitive. So what this is saying is that you should generate captions that uniquely describe the region of interest, taking into account the confusion set, because of this normalization constant in the denominator. So that just falls out of Bayes' rule. That's the only change we made. And now we just train the model to maximize the, so that's the speaker. So all we're doing is training the way we generate the text. And the speaker is going to receive that string, and he's going to do maximum likelihood decoding, because the prior is uniform. Okay, so that's it. It's a very simple method. Let me show you how it works. So before we could experiment with it, we needed a suitable data set. And there was a the prior data set from this group at UNC. I actually just had lunch with Alex Berg, and so it was, I think it was Tamara Berg who collected it. But that data had some issues, so we collected a new data set that's a subset of COCO, where we picked images that were ambiguous, where they had at least 2 instances of the same category. For example, we had, let's pick, this is a more fun one. Anyone who's worked on COCO data knows it's full of zebras. So we picked an image where we knew there was more than one zebra, and then we asked human raters, AMT workers, to describe this one as opposed to the others. And then one guy said, oh, the zebra looking towards the camera. Another one said a zebra third from the left. So they're quite difficult captions to understand. Okay. This data has been open sourced. So we train up the model, minimizing those loss functions I just described. And these are some token results. So if the speaker model, so if I click on, let's do zebras, no, actually let's do the pizza one. If I click on this pizza, it will spit out the string, the pizza on the left. If I click on this one, it says pizza on the right, which is kind of cool. Now, and then there are other success cases. There are also interesting failure modes. So here, if I click on this thing, it says a bus in the right, which has several problems. First of all, it's a train, not a bus. Secondly, it says in the right instead of on the right. Okay, that's just a little grammar error. We could fix that with a little bit more data perhaps, or tuning. And then the most interesting error is it says on the right, which it depends on the point of view of the speaker and the listener, right? So this model certainly is not capable of that kind of subtlety. I don't know of any current models that can, but you'd have to take 3D reasoning into account, and it's a good thing to work on. Probably people are. But this doesn't capture that. It's very superficial. Nevertheless, it works pretty well. So that's clicking on regions and generating text in a way that's unambiguous. And then conversely, given an image where there are multiple ambiguous regions, depending on the text that you type in, it can pick out certain bounding boxes. So if you say the giraffe behind the zebra that is looking up, it clicks on this one. The giraffe with its back behind the camera, it clicks on this one. The giraffe on the right also maps to that one. I think there were some folks in Trevor's group who extended this to do instance segmentation, I believe. So it's a very similar idea, but where it gives you masks instead of bounding boxes. So the spatial resolution of the decoder was improved. Okay, so that was stuff we did a while ago. That was an intern project with, sorry, I think it's Junma Mao, who was the first author. Now, one problem with that is that we had to collect a curated data set where we asked users to generate training data that describe one part of the image as opposed to another. And it's difficult to get that kind of data in the wild. There's already is a fair amount of data where there's just images and text, but the text is quite generic, and we'd like to leverage that. So, so that's one issue. The other issue is just a reframing. We could think about it as distinguishing a region within an image, or if you have a set of images, an image from a set. It's basically the same. But so the setup here in this follow-on work is somewhat similar. If I've got some ambiguous set and I want to refer to an element in the set, the baseline model that just does the max likelihood training would say an airplane flying in the sky, which would decode either. And this new model that we call the introspective speaker thinks about the listener's point of view and tries to generate something that is unambiguous but without needing especially trained training data. So in this example it says a large passenger jet flying through a blue sky, which refers to this image on the left.
Can I ask you a question about the previous?
Yes, of course.
Paper? So the objective function that you talk about, so the maximizing the probability of the region given the sentence, nothing in that, so that only cares about the ratios, of the likelihoods of the different regions, right?
Right.
But nothing in that encodes that it's a good description, right?
Yeah.
It's sort of like you could have a really, that could be very high for a very bad W, right? Like,
that is true, and that is actually an issue we're going to see in the next paper as well. So in the next work we added a grammaticality term as well. In this work we didn't, and we didn't need to, and I'm trying to figure out why.
It could be that the training data, because it's...
Well, you also have this numerator term, right? So you are looking at the likelihood of the word sequence given the region. Oh no, but this just sums to 1, yeah, so it's the ratio, yeah. If they were all equally ungrammatical, but somehow unique, it would still work. So yeah, you go ahead.
On this same slide, when you're saying, okay, I flipped the order of W and R, and then you need to normalize out across R, is that, I'm guessing that that's only possible because you sum over R, that there's a finite and fixed number of regions.
Yeah.
Is there, I guess I have one question background. Is the previous way that doesn't have that problem when it's like proposing, or is this I guess a new limitation that?
So actually there was I've forgotten the names of the authors, but there was a nice paper, I don't know, probably ICCV last year, where they extended this to, so we had a very small number of regions, like we ran a region proposal generator and picked the 10 most object-like regions, but they extended it to essentially a full sliding window setup where it was very, very dense. There were tens of thousands of candidates, and you can still, somehow using a dynamic programming trick, you can still do this efficiently.
Okay.
So it was very cool. So you get improved spatial resolution. And masks is another way, but that was still a finite set of masks. But the sliding window dynamic programming trick, if you email me, I'll dig up the reference.
Sure.
I really can't remember off the top of my head, but yeah, it would be nice to be able to go beyond. Even that is still bounding boxes, and it's things that you've seen. I should be able to describe like the red X on his laptop, right, for which there's no prior category even.
Yeah.
Right? That's tricky.
Monte Carlo bounding boxes and say, like, is this discriminatable from the rest of the bounding box? I don't know, it sounds hard problem.
Yeah, then I have to create phrases on the fly that really describe not just that. Here that's unique, right? Mm-hmm. It's not like there's more than one red cross. It's just I have to create phrases de novo to describe something I've never seen before. And to be honest, these RNNs can't do that. They're just memorizing the training data with a little bit of fuzz around the training set, right? All of deep learning is mostly glorified memorization currently.
Something
right.
Spit out unknown.
Yeah, obviously people are aware of this problem and working on it, but what's amazing is that it does generalize in plausible ways, right? But there's still, it's still easy to break this stuff.
Thank you.
Yeah. Okay. So the grammaticality thing, you'll see that coming up actually. So I think I mentioned this. So in this follow-on work, we wanted to do something very similar, but without having to train a model where we had collected discriminative captions. So what we did is, all we do is modify the speaker, but we only modify it at test time. So we train up the model, we just train up one model, a max likelihood image captioner. In fact, we took an off-the-shelf model. And we modify it at test time so that when it's trying to pick a sentence, S, given the image, it's going to try to pick one that has high likelihood, so it's grammatical, but also assigns higher probability to the target image as opposed to the distractor image. So basically, if the sentence is equally good under both, it will get penalized. That will sort of bias the decoding step to prefer sentences that are unambiguous but nevertheless grammatical. And this lambda term is some grammaticality trade-off that we set with cross-validation. And furthermore, since this is a autoregressive decoder, you can just rewrite this expression as a product of terms, one per time step, and then you can smoosh this into one equation here, and you get a term which you can just plug into your beam search algorithm. So it's very, very modular. You just change the cost function that you're optimizing at runtime, and that's all you have to do. So this is like a add-on to any existing model, which is kind of nice. And it works really well, even though it's super simple. I mean, it's two simple ideas giving good bang for the buck. So here is a target image, and here is a distractor. Actually, let's do this one on the bottom. If you run the naive model, it would say a herd of sheep standing on top of a grass-covered field, which describes both images. And our model with this slightly weighted decoder says a herd of sheep grazing in a lush green field, which clearly is a better fit to this one on the left. And so we did some human studies on this, and the humans like our captions much more than the baseline, by a big margin, actually. Okay, so that was max likelihood training. Yeah?
Yeah, so does this mean that adding more distractor images to the data set that you're training on makes your model more robust? Or
potentially. At test time, let's see. I mean, here we're just doing it with a pair, but you could imagine this as a set, right?
Yeah, my question is on if you move from a pair to having a set, is that going to increase the robustness?
Presumably, I mean, yeah, because it would be much more similar to the previous setup, where I have a sum over all of the regions, and now I want to pick something. Yeah, I mean, basically this is a special case of the previous setup, except that was baked into training, and this is just at test time. So, I mean, you could run in, I mean, if it's like the infinite, I mean, in the limit, right, where it's all possible images, well, then you get the finite sum problem again. But let's suppose it's just a large set, right? We don't worry about computation. You'd want to pick one that is unique to this particular image. So I think there has been follow-on work where people have done this with sets. I think one of Noah Goodman's students at Stanford is working on this right now with sets. Yeah,
so
not just pairs.
Sorry.
Go ahead.
It sounds like, so you said when you at training time you didn't you just did maximum likelihood training.
Yep.
Do you think you could do better if it were somehow able to integrate in the training objective, and you're going to have to disambiguate things, or?
Well, then you would need, presumably you'd need to know that I mean, then it's more like the first setup, right?
Oh.
Where you train on images where there is ambiguity, and you know which one you meant. Like you'd have to have a loss function here. We don't know which is well, I guess we do, because at test time we chose target and distractor. Actually, I mean, this setup where you have whole images doesn't require specialized training data, right? I mean, it just requires that the caption apply to both images. If you have a big set, then that caption might not apply to them all. So it's like if you get easy negatives, it's like if you're doing negative mining, you want them to be hard negatives, right? So if you pick images that are completely unrelated to the caption, I don't think it will make any improvement to the model. So coming up with hard negatives is kind of what we did by hand in the previous work, because we deliberately cooked the data that way. Doing that algorithmically, I don't know. And we could probably do it with feature matching or something.
Yeah.
In fact, it's been a while since I thought about this paper. The human study, we partitioned the data into easy and hard matches, where in fact, this is what this is Rama Vinay, I forget his last name. I'm going to mispronounce it. anyway, former intern, who's also a co-author of the next paper, he did FC7 or something and just clustered and then partitioned based on similarity in FC7 space. So that gave you visually similar or visually dissimilar pairs. So that's one way of creating hard or easy sets.
Okay.
There was a question at the back, yeah.
Going back to the other slide.
Yeah.
Do you think that if you increase the set of images you were trying to like discriminate against, you could remove the grammaticality?
The grammaticality term. I don't know. I mean, it's kind of similar to the discussion we had earlier, right? Like, as long as you discriminate well, then you don't need to be fluent. You could just say one word that's unique to the image and win.
Sure, but it seems like to some extent the reason that that term has to be there is so that it like says anything relevant to the images at all.
Yeah.
And if you have a large enough set, then the only way to get yourself anywhere close to these images is to say something relevant to them, right?
I mean, it would just have to be a minimal piece of text that would have higher, slightly, especially since we're maxing, right? We're not, it's a classification problem. If you're slightly over the decision boundary, I said one word that was unique to that image, and maybe that was the only word I omitted. I said yellow. And that's the only thing with the, or yellow bust, right? Which, you know, is grammatical, but not very interesting. So I don't know if discrimination power, no, even if this is a big set.
Assuming that the set like contained multiple yellow buses and stuff like that.
Oh yeah, if it has hard distractors, then you're going to be forced to say more. But here, I mean, this is a pre-trained model, so it's already trained to maximize the likelihood of the human data. So it is already pretty grammatical, and it's an RNN decoder that, you know, absorbs the language statistics pretty easily. Okay. So it's fairly fluent already. I mean, there was no retraining here. Yeah, it's an interesting question. But like, I think if you, so Noah Goodman I mentioned earlier, he's a professor at Stanford, you guys may have heard of him. He's done a lot of work on rational models of communication. And if the speaker knows that the listener won't understand what you're talking about if you're not grammatical, then that's kind of where the constraint comes from in an organic setting. So we're just baking it in here. But you can, if we had a proper model of the listener, it would fall out for free. And he has this sort of hierarchical Bayesian model that is a generalization of this, actually. Okay. Dawn, should I go until 2 or something? Yeah, okay, perfect.
We have the room until 2:30, so.
Okay, all right, that's fine. I'll talk about this work and then the new ICLR stuff. I'll be done by 2 for sure. So, okay, so the previous works were basically sort of tweaks on existing max likelihood training methods. But there's a problem, well, we know that image captioning is ill-defined. But there's a problem with just generating fluent strings, right? And copying what the human said, because there's many ways of saying the same sentence, and it might not be very likely according to the ground truth human set, but it still might be a perfectly good description. So measuring the quality of these descriptions is a problem. So there's various automatic metrics in the literature, mostly coming from the machine translation world. So Blue and Meteor come from machine translation, and CIDR was developed for image captioning, and then there's this new thing called SPICE that was proposed by, in this paper here, 2016. And what these plots show are the automatic metrics on a bunch of image captions versus what the humans thought of these captions. And what you see is that the machine-generated captions often score higher under the automatic metrics than humans think they should. So the human captions are apparently worse than the machine captions, even though they're obviously better. And that indicates a flaw in these existing metrics. So the SPICE paper came along and said, okay, we have a metric that finally correlates with human judgment, where humans are ranked higher than machines, as it should be, in this problem at least. So the way it works, do I have a slide on that? Yeah, this is roughly how it works. They take the caption and they parse it, and they build a little scene graph out of it. And since these captions have since these images have 5 captions in the COCO data set, they can aggregate little scene graphs to build one big scene graph. And that's ground truth representation of the meaning of this image. And then your algorithm comes along and generates some text. And it goes through the same pipeline. They parse it, they build a little mini graph, and they do graph matching. And the SPICE score is some metric for comparing graphs. And I forget exactly how it works, but you know, they're normalizing the word forms, and there's points for matching nodes and edges and so on. So we literally use it as a black box. They have like a Java binary on the web, and we just treated that as a black box, and we want to optimize that, because that is shown to correlate well with human judgment better than any other automatic thing. And we don't want a human radar in the loop when we're training. So, so this seems like a good metric, right? So because good captions score high. But we'd also like it to be the case that if we directly optimize that, then we would get good captions. So we tried optimizing for SPICE. SPICE is a black box optimization function. So we're going to use, it's coming up, yeah, we're going to use reinforcement learning to optimize this. And this had been proposed in prior work. So it's just, so the setup is the following. When I first heard of this, I thought this is weird. It's not an RL problem, but you can think of generating words as a sequence of actions, and then when you finish creating the sentence, you're done, and you call the oracle, which is this Java code, and you say, hey, how did I do? And it gives you some points. So that's like your reward function. And so the language model is your policy, which is choosing actions or words at every step. And the state space is the whatever state space you want to pay attention to, so the hidden state of the RNN and any image features that you condition on. So that's the setting. I don't know if you guys have gone over this, what kind of RL stuff you've done in your class.
Nothing yet.
Nothing yet. Okay, so you'll see more of this probably, but this is the policy gradient equation. So we want to take gradients. We have a value function, which is the value of being in the current state in our MDP, and I'm not going to go through this because you'll probably do it in more detail in another talk, but you can write down the gradient of that expression as this thing here, which is basically saying what's the expected quality of being in this state compared minus some baseline, which is on average how well do you do, times the probability of taking that action. States are, what is GT? GT, oh, is the word that you're generating, right. So what we're going to do is a bit like these tree search algorithms. We have beginning of sentence here. We're going to do Monte Carlo rollouts about possible sentences. And we're going to roll them out until our policy says stop. We get an end of sentence symbol. And then we're going to evaluate the reward. And we're going to do that a few times and get a stochastic estimate of the quality of the sequence of actions we took. And then we're going to wiggle the parameters slightly to make the highest scoring sequence more probable than the low scoring sequence. So it sounds really slow, but in fact it's not too bad, because the cost is sort of dominated by the feature extraction on the image side. And these rollouts are pretty cheap. It's like twice as slow as ML training, which is not really a big deal. A bigger deal is controlling the variance. So we have this baseline. So we're looking at relative gains compared to the baseline, which is the average performance. There was a prior work called Mixer from some guys at Facebook. And there are two main differences between our work and theirs. First of all, when they estimated when they used the policy gradient method, they didn't do this Monte Carlo rollout. They had like a fixed estimate of future reward that didn't use the model, so it was less accurate. And then secondly, they were optimizing BLEU score, and I would argue that's the wrong thing to optimize because it doesn't correlate with human judgment. We're optimizing CIDR score or some variant of that. But we can optimize BLEU. If we do optimize BLEU with our method, we work much better than Mixer. Because we do this Monte Carlo rollout, we have a better baseline estimator. And so we compared head-to-head with the Mixer thing on the same model. It's the vanilla model. And if you optimize the BLEU metric, or you optimize some combination of BLEU, CIDR, Meteor, and Rouge, which are the ones that are used to measure performance in the COCO competition, you can win that competition even with a really dumb model. So the previous winners of this competition, people were doing bells and whistles with their models, with attention and so on. And at least briefly, for like 1 or 2 months, we were #1 on the leaderboard. I think we're still in the top 3, even a few years later, but we have been surpassed. I think in your reading list, the winning paper is in your reading list. And they use something very similar with an improved baseline estimator. But more interestingly is if you show these captions to humans, they don't like them very much because we're optimizing the blue score. If instead you optimize SPICE, the semantic parsing thing, it works better, but they're not very grammatical. It turns out. I wonder if I have examples of that. Yeah. Let's see. So here, this is max likelihood training. So this is the previous stuff you saw. If you directly optimize the SPICE score, it will generate a red double-decker bus on a city street, on a street, with a bus on the street, with a bus on the street, in front of a bus on. Right? So it's not very fluent. And the reason is, when you do semantic parsing on that and build a graph, it doesn't really matter if you're not fluent, as long as you get good graph coverage. Right? So what we did is we realized that optimizing directly for this wasn't good, so we just did a convex combination of SPICE and SPIDER, which is the best previous syntactic metric, and we called that combination SPIDER. And that was the that metric generates nice sentences like a red fire truck is on a city street. Or here it says a group of people walking down a street with a traffic light. And so we did a user study, and humans like the captions that were generated by our method to optimize SPIDER significantly more than if we optimize blue score. And both of these improve upon the standard method of max likelihood training. Cool. So, so that was that. So this is also quite modular, right? It's a very vanilla model. You could presumably get better results with a better model, and of course more data, but I think the metric is very important. In my opinion, a lot of the interest right now in RL is not because, I mean, obviously there's applications in robotics, but it's really because it allows you to optimize arbitrary black box objective functions, which are closer to the tasks that you care about, non-differentiable objective functions. Okay, any questions on that? Yeah.
This is like more of a very specific question, but on the like blue, on the like MLE generated caption for like, the fire truck thing.
Yeah.
Why does MLE say, or like this might be a hard to answer, but like why do MLE and SPICE go for bus when like every ground truth caption contains fire truck or like fire engine, and then like it seems that Mixer is going for fire truck or at least red bus, like red fire truck. Seems like it's just ignoring what is in the ground truth caption.
I mean, it doesn't see the ground truth caption, right? I mean, guess this.
Oh, right, okay.
Yeah, so it just sees image features. So they have all of these models, of course, are the same. It's the same architecture in every case. Or the only thing that's changing is the objective. So somehow the objective is forcing it to pay more attention to some things than others. I don't know. We didn't try to like introspect inside of these models. I mean, other people have done it. With the attention models, it's quite a common game, right? To see where any image is looking at. I'm not sure that really describes the differences that you see in the behavior of the models, but we did not do that here. All right, so the last thing is joint models. So, yeah.
I guess when I read this paper and I was actually kind of interested, I mean, do you think that this approach of policy gradient, like, you know, like on a just any sort of sequence task, like natural language task, do you think it should just be used whenever you would want to do a maximum likelihood supervised learning problem?
So there's several caveats. So one important thing I forgot to say is we pre-train this with maximum likelihood. So this is such a high variance estimator that it doesn't really work if you just use it. So we do MLE training and then we fine-tune it with policy gradient, and everyone does this. And it's a dirty little secret that RL like doesn't really work right now. I mean, it's very, very difficult to make it work. And so I mean, max likelihood training is a good bedrock to build on.
Do you think the fine tuning should just be done? This policy gradient fine tuning should just be done every time in general, or?
I mean, if you have the right objective. Otherwise, like if we optimize SPICE, it was working worse, right?
Yeah, I guess. Yeah.
So.
Okay.
Yeah, I think it depends on the task. Okay. All right, so this is more recent work. So the captioning stuff's nice, but you know it requires supervised learning, right? So we need labeled pairs of images and text. It'd be nice to learn from lots of unlabeled images or lots of unimaged text, as it were. And it'd be nice if we could do it symmetrically, right? If we could generate language from images, but also vice versa, just for fun. But also, I mean, it is cute to generate images from text, but I think also it's a way of diagnosing what the model really understands. That's sort of my interest in it. So this is sort of the grand goal, is that we'd have some latent representation of the world. I think that's what we're after in AI. And then these are just signals that views on the world that we'd like to interpret. So if you have this joint model, you could go, parse the image and get a representation and describe it, but you can do the opposite as well. So we're going to focus on this latter pathway, although it's a symmetric model, so we could do image captioning as well. So we'll build on a common framework that's popular now, which is the variational autoencoder. Is this something you've gone over in class?
We haven't, but it's in the prereq classes.
Okay. Yeah, everyone should know this. I think this is, well, I don't want to say it's more foundational than the other stuff, but this is all pretty common at this point. Who has not heard of VAEs before? Everyone's done. Everyone met your prereqs. Everyone, I think, bar one. Anyway, so this is a fairly simple extension where we have two observed kinds of features. So we have images and text. And because it's a directive graphical model, it's going to be, in principle, easy to train when we only observe X or only observe Y or have both. So we can do semi-supervised learning. Now, we want to be able to infer the posterior given the data. And so if we observe X and Y together, we can just fit an inference network in the usual way. And this is basically identical to a standard VAE where we just concatenated X and Y. But we also want to, oh, I don't have a picture. We also want to be able to do inference given just an image or given just text. So we call this one image understanding and this language understanding. So we're going to use the paired one for training, and then we'll use these at test time when we only observe one modality or another. Or if we're doing semi-supervised learning, we need these unimodal inference networks. And now we need a way to train all three of them. So we propose this new objective called the triple elbow, which is 3 elbows put together, elbow being the evidence lower bound. So the standard setup for a VAE, if you just squint and concatenate X and Y together, this is the regular objective function with a few scaling factors. So it's the expected log likelihood of the data minus the KL term. And now we add on 2 other terms, one for images and one for text. And then we just mix these together. Right? So this is a pretty natural thing to do. And you can think, yeah, so that, I don't want to elaborate on that. The other twist we made is we want to be able to do inference about the world given uncertainty about or given partially specified descriptions. So the original goal was the following. So if I start speaking to you and I say like a woman, then you will conjure up something in your minds, and there's all kinds of scenes that are consistent or world states with that partial sentence. And if I say a woman is running, then the posterior entropy in your brain shrinks, and now you have a more concrete idea about what I'm talking about, but there's still a large space of possibilities. And if I say is running with a dog, and then that narrows it down. And it's similar to that set naming stuff I talked about earlier, right? So we have the space of possible worlds, and as I say words, then my uncertainty should shrink. It might also expand. It's not necessarily monotonic when you condition on data if it becomes ambiguous. But in general, the more bits you observe, the less uncertainty you have. So we wanted to handle an inference network that can handle missing data, which hadn't really been studied very much before. So in our setup, our text is simplified. It's just an attribute vector. So those who know the Celeb A data set that I'll show shortly, it's like faces that are described with 50 attributes, male or female, beard or not, glasses or not, brown, black, yellow hair, whatever. So you can imagine that as a categorical vector, and now you can reveal a subset of those bits. And the more bits you reveal, the less uncertainty you have. But if you don't have many bits, you're going to be very uncertain. So what we did, there's this paper from Chris Williams. Actually, we published the work first, and he told me about the paper later. But in the linear case, you can derive the exact posterior for linear factor analysis as a function of how much data you're missing. It's straightforward. And it has this property, which I just described, where if you condition on more, your posterior entropy shrinks, right? So, and that is basically a product of Gaussians. You get 1 Gaussian for every bit that you observe. And they multiply together and you normalize them. So pictorially what's happening is let's suppose I say, this is woman here in the blue curve. If I say woman, it shrinks you somewhere in space. If I say running, it gives you the red curve. And if I say woman running, it's the product of those two Gaussians. It's sharper, right? Because I'm giving you multiple constraints on what it is I'm thinking about. And in 2D, you get this picture where we might be specific in one dimension, like this x dimension is quite narrow and the y dimension is quite broad. And then this expert, when the bit referring to running or not, is a different part of latent space. And if you combine them, then you carve out this constraint where both have to be satisfied. So basically our inference network we define to be this product of inference networks 1 per attribute. And we're just going to combine the posterior for the bits that we see, and the bits that we don't see we ignore, which is the right thing to do when you have a directed graphical model. And I'll show the effects of that in a moment. So we call these abstract concepts because we only partially specified some of the bits. If you specify all of them, they're fully specified. I don't think I have a figure in the slides, but we had this, let me make it concrete. We did first experiments with MNIST. So we had a concept hierarchy where we had like a digit, and then it could be, it could be the location, so it could be top left, or top right, bottom left, bottom right. So you could split on that. Or you could split on the class, right? So it could be an even digit or an odd digit. Or it could be even and in the bottom left, right? Which is a conjunction of that concept, and so on and so on. And then eventually you get the leaves of the tree, or the DAG rather, where all of the bits are specified. So here I'm specifying parity, here I'm specifying location, here I'm not specifying anything, right? So I think of it as like playing chords on a keyboard. So here, this is a new data set we created. It was surprisingly difficult to release this because we don't have rights to MNIST. So the Google lawyers wouldn't let us release the bit. So we released a script to regenerate it yourselves. Crazy. All the code for this is so this paper, we released all the code, and then a group in Montreal reproduced it as part of their class. So Joël Pinot's running a class called Reproducibility and Deep Learning. And we were very happy that the students were able to reproduce all our results, and the reviewers liked that as well. But releasing the data was harder than releasing the code. So here, so we had 4 attributes: the number, the size, the location, and the orientation. Okay, so so we can train up models with these little bit vectors and these images, and now we can test the model. And the other thing we propose in this paper is a way to test generative models of images in a generic way that's independent of what the model is. So we talk about the 3 C's of visual imagination. So one of the C's is correctness. If I tell you to generate an image that has 4s in it that are big, upright, in the bottom left, then all of the images that you generate better have 4s that are big, upright, in the bottom left. So they're correct. They all satisfy the constraints that the query specified. But there's going to be some variation, right? Hopefully. We'll talk about that in a minute. Other methods don't do as well as us. I think I omitted the comparative work in these slides, but it's in the paper. Obviously people looked at joint VAEs before, right? But our objective function is slightly different, and we show it works better. The second C is compositionality. So this is more interesting. So I should be able to give it a query that I've never seen before, some combination, and it should still do the right thing. So we trained on a subset where we gave it, like, I forget exactly what, but maybe we gave it odd digits that were big and upright, but it had never seen even digits that were big and upright. It'd seen big, even digits that were small, but it had never seen even digits that were big. And it had to learn separately the size and the shape. So here it's interpreting this query correctly. And how do we know that? We trained attribute classifiers. So we generated these images, and then we had pre-trained a set of Oracle attribute classifiers. It's a bit like a discriminator in a GAN, but it's fixed. And then we just ran it over the generated images, and we asked what fraction of the generated images have the attributes that we specified in the query. So we can measure this automatically. And then the last thing was coverage or diversity. So if I give you a partial query, then I want to get some variation. So if I just say, generate me something in the bottom left, then it's going to give you some 0s, some 3s, some 9s, some 8s, and the 0s have different styles and so on. So it's giving you, this is related to the mode collapse problem in GANs, but this isn't specific to GANs. And the key thing is here, this is diversity as a function of the query. So if I fully specify the query, I don't want any diversity. I've narrowed down the concept specifically. So now they were sort of looking at different criteria. We can walk through this abstraction hierarchy that I was sketching on the board. So we can say something big, bottom left, and then we can add an extra bit, and we say I want it to be 8s, and now I want them to be 8s that are counterclockwise. And we can sample from the model as we condition on more bits, and it's doing the right thing, more or less. Or at least it's doing better than others. And then the last thing we did was to apply it to celeb A, which is again just image patches and attributes, but they're real images and they're bigger attributes. So this is a subset of the hierarchy. Let's see. Right, so it was trained on fully specified bits, and then we're going to query it on abstract queries. So we're going to say, generate me some images of black-haired people, and here are some sample images. And it's good, it's right, it's got men, it's got women, there's some diversity there. And then we say black-haired, not smiling, and none of them seem to be smiling, which is pretty rare for this data set because they're all celebrities. And then we say black-haired, not smiling female, and they all look female to me. So it seems to be doing the right thing. It's qualitatively similar to the MNIST data. And the quality of the generated images is reasonable, right? I mean, you could get higher visual quality with GANs, but that's a whole separate can of worms. And here's a comparison with some other methods. This is the joint multimodal VAE, and this is the bi-variational canonical correlation analysis. And I forget the authors of these papers. But visually, you can see that bi-VCCA just doesn't work at all. There's like no variation at all. It's like mode collapse for VAE due to the way it's trained. And the JMVAE actually does pretty well. It's similar to us. We're generally better, but they do quite well as well. And let's see. The other thing you can do is you can probe it, right? You can say, the paper was called Visual Imagination, so we want it to generate things it's never ever seen before. So we can say, generate me images with glasses. And then we can say, every image has glasses, so that's good. And then we can say, generate me images, and I don't care if it has glasses or not. And none of the images have glasses, so it wasn't really giving us a lot of diversity. And that's because in the training data, almost nobody wears glasses. So, you know, it is a max likelihood training criterion, so it's picking up on data set bias sort of implicitly there, which of course is a very hot topic. And then finally, this is the novel generation thing. So we give it a query it's never seen before. We say, generate a bald female, and this is what we get. It's a little scary, these images. This is what the rival method gets. And if we look at the training data, let's see. I have to remind myself what this is all about. There are some right, so there are some images that are labeled as bald females, but none of them are bald females, right? So this is label noise, it turns out. It's a very rare combination. And I think that's in the test set. I don't remember exactly. I should refresh myself. Anyway, so that's what we did in that space. So just to finish, I started with this slide, and I didn't really deliver on this slide because we didn't really model scenes, right? We just modeled image patches. And we didn't really model sentences, we just modeled bit vectors. So there's clearly more work to do here. And our representation of thoughts was just a vector in Rn, right? Which is not really a very interesting representation of the world. So there's clearly more work to be done here to model compositionality and structured representations in latent spaces, and to scale it up so we can really do semi-supervised learning, which we can in principle but didn't actually do. So yeah, I think this is a fun area to work on. Cool. Yeah.
Can we go back one slide?
Yes.
Do you have thoughts about how you would go about anchoring the the latent representation in a more interpretable form, or or if you wanted interpretability, would that make more sense as sort of another input view of the?
That's a very interesting thought. So I've considered both. I mean, you could imagine imposing your beliefs about how the world is in your latent representation, like a scene graph, right? Like in the work on the visual genome, and then force that to be decoded into pixels. Or you could just view that as a form of human annotation, that you're completely agnostic about what the latent representation is. Maybe it is just a vector in Rn. I mean, the brain is just a bunch of neurons firing, right? But the scene graphs induce constraints on that. I don't know. I'm a little partial to the first. I kind of like my representations to be structured. There's this very nice paper called The Structured Variational Autoencoder by Matt Johnson et al., where they, it's great to be untethered. Well, the example in their paper is they took a model that's near and dear to my heart. So it's a switching linear dynamical system that's evolving over time. So you've got some discrete states that specify what mode the system is in. And then you've got some continuous dynamics. And then it generates images. And these were images of like mice running around a cage or whatever. And this is actually a nice interpretable model. And if this was all linear, you could do common filtering, common smoothing on that. But this is some nasty neural network that's really hard to interpret. But all of the complexity in the pixel space is buried here. And this is like a simple semi-linear model. So I like this combination. It's like a semi-parametric model, right? I mean, it's technically parametric because this is finite. But this is not even required to be interpretable. But by design, they wanted an interpretable latent space because they were doing scientific studies of these animals. So I could imagine something a bit like that, where you have a rather rigid prior that is forced to be interpretable and is like sample efficient, and then you soak up all the remaining complexity in a black box neural net likelihood function.
Yeah, that makes sense.
It's just speculation there. Come do an intern, we'll work on it. Yes?
So you said that the BCMR metrics comes from machine translation, right?
Yeah.
So you came with Spicer.
Yeah.
Do you think we can apply Spicer metric to machine translation or other NLP subtopic?
Yeah, I guess so. I mean, absolutely you could, because they don't actually use the image at all, right? All they do is they take the ground truth captions and parse it into a graph, and then the generated caption and parse that into a graph and graph match. So you could totally use this for comparing sentences without images. They only use the image to ground the sentences to be about the same thing. So as far as I know, there's nothing else that's specific to images in this particular metric. That's a great idea. I don't know if anyone's tried that. I don't know much about like natural language semantics and metrics on that. Yeah.
Just curious, what did you use as your feature network for captioning?
Oh, something standard. I don't know. ResNet, Inception, I don't know. Whatever they used in the prior mixer paper. Something, it was I don't know, it was a long time ago. I guess it was pre-trained on ImageNet. These are small data sets, right? So it was some standard thing, might have even been AlexNet.
Probably VGG.
Yeah, it was probably VGG, yeah, because the weight's already there. And so we didn't even...
No, you're Google, sorry.
No, but we were using the same model as Mixer, right? Mm-hmm. And because they're Facebook, but they were using the same model as whoever, right? So all we're changing is the objective function. I don't remember. It doesn't really matter. Maybe it matters. It does matter. I should take that back. Of course, better features matter. That was a little clip. For the purposes of comparing these metrics, it doesn't matter. I mean, everyone benefits by better feature extractors. That's obvious. Yeah.
When you were trying to generate novel stuff, on the celebrity data set, we saw that some of the descriptions are mutually exclusive, like black hair, brown hair, blonde hair.
Yeah.
You didn't talk about what happens when you try and, I guess, get like mutually exclusive things that don't make sense but are still novel.
Yeah. So we good question. So we use a subset of the attributes. There's 50 attributes, I think 50 or 40, I don't remember, in Celeb A. And then there's another paper that selected a subset, I think, of 18 that were more or less mutually exclusive, orthogonal, and were visually descriptive. And then we just hoped that they weren't mutually exclusive. And we trained here, I think this is just a qualitative study, so we didn't even bother training attribute classifiers on it. I mean, obviously there's a lot of work on attribute classifiers for Celeb A. But yeah, you're right. I mean, we could ask it to generate, I think we grouped the hair colors into one. So these are binary. I think we grouped them into categorical, so they're forced to be mutually exclusive. And we did that by, well, we talked about doing it. To be honest, I can't remember if we did that, and then, or we just treated it as binary and ignored the problem.
Okay.
I don't remember. But it's an issue. But you know, that's I mean, more generally, right, with imagination, you could say, okay, I want you to imagine, I don't know, all kinds of things that are impossible, not just physically, but then contradictory. It's the empty set, right? But
I guess I'm just curious, you know, like on this, you know, product of experts, like if you end up with a Gaussian that, you know, like shrinks to absolutely nothing, like what happens?
Yeah, that's a great question. So we did find, I skipped over this because I thought it was maybe too much detail, but so this is an interesting thing. So in the product of experts, the original paper from Hinton in 2002, you have a fixed number of experts, you always multiply them together, and they vote for what features they think are present and what constraints they want to impose. As you remove those constraints, you end up, and what matters is that the product of those Gaussians is well defined and generates the data. If you remove those constraints, you might end up with a very poorly conditioned Gaussian that's floating around, that doesn't have high likelihood. So what we did is we always multiply in what we call the universal expert, which we just set to be the prior. So now it's always relative to this prior. So we have this nice, well-conditioned Gaussian, and we're just basically carving pieces out of it. And it becomes narrower and narrower. But if you specify nothing, it defaults to the prior. And then if you generate from that, it will give you models from your prior model. And so we needed that to get good coverage and to make it numerically well-behaved. And it makes sense intuitively as well, I think.
So the form of composition that we have here comes from this Cartesian product of different attributes. The kind of composition you have in language is even, you know, potentially richer. And, and you, for instance, you can like negate stuff, or single words can sort of rearrange, change how you parse the whole sentence. And are there like sort of natural extensions of how you of this kind of composition? You know, with sort of ways of like including richer kinds of composition in this product of attributes, or
I don't know. This seems, I mean, this seems rather specific to this setup. I mean, usually with natural language text, people are using RNNs, right? And it's not clear how the state of the RNN encodes more or less precise concepts. Right, if I give it a short, I mean, people will map an arbitrary length sentence to the same fixed length vector every time, right? It's always, whatever, 256 numbers, no matter what I said, even if I just repeat myself and stutter. I mean, where you are in space will change, but not the uncertainty. Now, who knows, with a neural net, I mean, this covariance matrix is just a vector of numbers as well. I'm interpreting it as a probability distribution because sort of it kind of baked into the model, but maybe the RNN uses some of the latent dimensions to represent mean and some to represent variance. I don't know, but there's nothing in the training to sort of force it to do that. Yeah, I don't know. I mean, I haven't seen any prior work on this. And I don't know how to do it, actually. To do it, I mean, we wanted to do it with natural language, of course. Attributes is just a hack.
Any other questions? All right, let's thank our speaker again.
Class dismissed.